Well, I'd like to introduce myself by first saying that global warming is here. I have proof of it. I want to hand it out, let you see global warming in person. Global warming. You can hand it around. It's hit us, so accept the fact. We go forward. Actually, I acquired that in Boulder, Colorado, some years ago, before it had become more accepted that global warming due to human activity was occurring. So it is there. Now, maybe I should say just a word about why I'm here talking. It's because I became very concerned some years ago about the need for public literacy in the whole topic of global climate change, because there was a lot of press going on, a lot of debate, even some scientists were debating each other, and it became clear that the understanding of the scope of the problem was pretty limited. And I think it's very important that we have a better educated public. In fact, I felt so strongly about this that I went and devoted time to producing this textbook, which is really designed for meteorologists around the world, particularly in developing countries, because this is not just a rich man's problem or issue. This concerns all of the humanity of the world, because they are all helping to create the conditions for the warming, and they will also face the consequences, whether they be good or bad. But there could be consequences. My own background, as Jim said, I have done research and climate work and modeling work for many years. My focus was on natural variability. It was not actually on the climate change. By climate change, we're referring to changes due to the impacts of humans. So I basically want to share my thoughts on this, but I want to make sure there's a lot of room for questions, because part of this is to make sure that we're talking the same language and I'm answering some specific questions that you might have. So we'll allow plenty of time for that. Now, to give a little bit of, if I can get this thing turned on, there we go, perspective on this. As the title says, we're going to look at a number of issues. Let's get this lined up here. That's pretty good. No, it's crooked. Let's just do it this over here. There. Can you all see that? Okay, basically, as the title says, we're going to just go through these topics, and I really want to start out with what unconvinced people say, because I have over here on the table a number of headlines on newspapers. Guess what? Antarctic's getting colder, not warmer. This is in actually the Christian Science Monitor. And here's another article. Disease threat cited in global warming. Well, that's a statement of things that are happening, which is perhaps not misleading. Here's another one. Hot air is bad for us. It's amazing the kind of headlines one gets for this business. So what I want to do is just spend a minute looking at a few examples of these statements that people are making and make some comments on them. So we'll put this up here. These are just some quotations I took. Theory remains entirely unproved. Well, the word entirely, of course, is the one which is showing that it's a very misleading way to describe the situation. Number 2, 1 in 3 chance that the experts are wrong. This is what it says in the paper. And of course, the paper could have said 2 in 3 chances that they're right, but they chose the one which had the word wrong in it, because this is part of the way the press works. It just tries to tilt things here and there to achieve what might appear to be other agendas. Models are incapable of handling water vapor. And of course, this is just an outright falsehood, and I don't know where the writer got that idea. Troposphere, which is the upper atmosphere, should be warming faster than at the surface, and it is not. It's not, and it's not, which is consistent with the global warming theory of the greenhouse effect. If the weather folk can't figure out what's happening for the rest of the week, how can they tell us what the climate will be for the next 50 years? Now, you might think you got me on that one, because we know that the short-range forecasting for weather, has certain limits, and certainly much less than 50 years. But this all depends upon understanding what we mean by global climate in the first place. It's not the weather at a specific location at a specific time. It's the average of conditions over a long time and over large areas. And basically, we're not trying to predict whether or not there will be rainstorm in Madison in 5 or 20 years on this date. We're trying to predict what the average conditions will be in 50 years. So it's a different type of forecasting thing that we're dealing with. Some of this arose out of the fact that in New York City, there was a prediction for a big snowstorm, and it missed. It missed New York City and went slightly to the side meaning maybe 100 miles away. Well, of course, from the point of view of the New York people, it was a miss. But from the point of view of the overall climate system, it wasn't, because the storm did occur. It occurred near where it was predicted, and it was part of the general picture of storminess, which causes the general average conditions that occur in the atmosphere. And here's the one I did mention. Guess what? Antarctic's getting colder, not warmer. Well, if you read this article carefully, it goes down a ways in the article, and this colder was referring to observations at one point, or some conditions in part of Antarctic. It went on to actually say that the majority of stations in Antarctic were actually showing a warming. But the headline says this. And then you have to again remember that if you talk about a single point in time or space, you can always have colder or warmer. There's a lot of natural variability in the system. And the fact that one station is getting colder does not maybe mean that the general conditions are not in a warming stage. Because even in the last 100 years, there's certain places in the world which actually have gotten a little bit cooler. At the same time, many more have gotten a little warmer. Finally, global warming is still just a theory. Well, that's just another statement in the press. So those are some examples of what is said, and what I'm hope by the end of the evening you might have a better perspective on the whole issue and maybe be better able to make judgments. Now, what I want to start out with now is a list of facts, finding things that even the naysayers will not disagree with, because it's important to know some things which are the case for the global warming condition. So I'm going to look at these facts here, and this is in that handout that is floating around. Statement about the mean temperature has been going up. This is the global mean surface temperature has been going up. We'll look at that. We'll also confirm that the amount by which it's going up does not exceed natural variability. So we're still within that limit. We can confirm that the carbon dioxide has been going up, and that has a very direct relationship to commerce and manufacturing. We can also confirm the theory, which people agree is important, which links this carbon dioxide, etc., with the temperature. And another fact here is that climate change is just not a Madison issue. It's just not an atmospheric issue. It goes into what we call the whole Earth system, which is a far more complex situation for any of us to comprehend, let alone the non-scientists. And of course, one of the facts of the whole issue is that there are a whole array of uncertainties in the picture, and I will give some perspective on this. And by the time I get finished with this one, you might figure this hopeless. It looks so uncertain. There's so many questions and problems that we should give up. Well, we're not giving up, but it will take some real effort to proceed. Finally, another fact is that there's been several thousand scientists actually focused on studies directly related to climate change. I brought here just one of their reports in just one section of the climate change issue. You see, it's a huge Bible or phone book looking thing. And of course, for anyone to really get an understanding out of this, it's pretty impossible. And this is just one of many. If I showed you the reports that were issued just in the past year, every 5 years there's a series of these, it would stack up about that high. So that's sort of a measure of the complexity of the whole thing. But the other thing is that there's scientists from many countries involved, over 40 countries involved. And in the United States in particular, for this book here, there were roughly 400 American scientists just involved in the review process, not the writing, but just the review process. So you can't say this is a foreign intrigue. Someone else outside the U.S. is trying to do things to us, because the U.S. scientists are very strongly into the whole process. And so what we're talking about now is a building consensus that has come out of these people who've really focused on the problem, which defines where we stand in terms of scientific understanding. Okay, now let's look at the some of the facts and specific facts, and you maybe have seen this type of picture. This is a statement of the global mean surface temperatures measured over the Earth for each year since 1860. Commonly, we go back 100 or 150 years because that's sort of considered the beginning of the time when the human activity became general enough across the world to have an impact on the larger scale systems, not just the pollution in the city, but the larger scale aspects, which refers to the climate. So that's sort of the beginning of the record. Now, what we have here are just the temperature, average temperature for that year compared with a reference time, which is over in here. So you can see that it was below that reference temperature here and gradually goes to above that reference here. There has been a trend in temperature in this record estimated at something like half a degree Celsius since the turn of the century. Now, you might look at this curve and say immediately there's a problem. There's a problem because from 1940 to 1975, the mean temperature went down. And I just mentioned that we're going to relate the carbon dioxide and other greenhouse gas increases to the temperature increase. And now we see this going on. Even at a time when the carbon dioxide was increasing, you might say, well, there goes the theory. But this, you have to recognize that there's a lot of natural variability in the system. A lot of natural variability. And this, in fact, has been related in part to solar changes in the solar condition. And so, and these other things, sunspots, and there's a number of things which can affect this, volcanic activity, so on and so forth. Now, on this diagram, we have these lines. We also have the uncertainty. The uncertainty in the estimate here, it's sort of hard to see it. It's a little bar. You sort of see half of the bar sticking out here beyond the colored section. Notice for the old data here, there's big uncertainty because we had a far less complete observing system throughout the world, over oceans in particular, whereas in recent times the uncertainty in this measurement has become much less. So we always try to be honest about the uncertainties in these, but even given that, you still see that there has been an upward trend in the temperature. Now, I said it was roughly half a degree or Celsius has occurred. If we look at the big picture, for temperature variations due to human presence, we look here at this line on this temperature curve. Here's the present condition for global average mean surface temperature. And some of the theories, we'll get into this more later, project an increase of maybe 3 or 4 degrees Celsius plotted right here. This is sort of a measure of the type of variation in global mean temperatures that we're talking about. Yet, if we look historically here through the ages, we see that the temperature, in fact, was warmer than this and colder than this in the past, and the temperature variation is more than this 3 or 4 degrees that we're talking about here. So this is all natural variability. So we have to remember this all the way through. Now you might say, well, this really proves it's not important. But some things you don't see on here is the time scale. If the time scale over here is like 100 years, with the time scales that we've plotted these things is thousands or 10,000s or millions of years. In other words, overall, the change occurs over a very long time, which really allows for the system to have a certain rate of adjustment, whereas this change is projected to be rather quick in terms of ecosystems, et cetera, et cetera. And that's also a difference. And of course, we can argue that the human race really wasn't around in here, so we're not accustomed to how to live when the temperatures may get to that level. So that is sort of the second fact. Now, if we look at the green, I mentioned the greenhouse gases are increasing, and these are measurements. Measurements. There have been some direct measurements back more than 100 years. There have also been some indirect measurements looking at air bubbles in ice and sediments and what other. They've come up with estimates for the concentrations of these greenhouse gases here, starting from year 1000 to the year 2000 in here. And you can see, starting with the industrial age, I said roughly 150 or 200 years ago, we get this exponential increase, which is directly correlated with the amount of CO2 estimated to be put into the air from our factories. And so we have the increase here from 280 units to up here to 350. Hasn't doubled yet. But methane, which is another greenhouse gas, is increasing, and so is nitrous oxide. So that's observed. That's the fact of the system. Yes?
How do you measure? I mean, how do you know how much nitrous oxide is in the environment?
Again, I say we're talking about what people do by analyzing ice in layers below the Earth. It's like geologists can go down and find out about the past, or paleoclimate people can go down by looking at. There's a whole line of methods they use, and I'm not prepared to elaborate on them. But that's it. It's an indirect method. Obviously, we don't have direct measurements before in here.
So ice cores and things like that.
Ice cores would definitely be part of this, and they can tell things perhaps by sediments at the bottom of the ocean. I'm not prepared to get into that one. There's a lot of different fields that come into this discussion, and no one person is going to be able to deal with too much of it. We depend upon talking with each other as scientists. The one other gas I show in here is sulfur. The sulfur is not a greenhouse gas. In fact, it has effects which are sort of opposite in terms of the atmospheric surface temperature condition. But notice here, we do again, starting at roughly 1800 or so, the increase in sulfur. But notice it stops. It increases to a maximum, and then it's going down. So and this is produced by people again, industrial production. But we are able, cleverly enough, to cause a change in the concentration due to concerted actions, cleaning up the smokestacks and things like that, which means that there is hope, that humans are capable, if they want to, perhaps to reverse some of these trends that we see in these gases. And so that is a point of optimism. Now, another fact is the greenhouse theory, and I don't want to get too deep into science here, but we talk about the greenhouse effect, which relates greenhouse gases and their concentration to the temperature throughout the atmosphere, average temperatures, including at the Earth's surface. The key thing about the relationship here is between radiation in the atmosphere and the energy level of the atmosphere measured by its temperature. And it's the radiation which is primarily responsible for determining how the temperature varies in the atmosphere. There's two forms of radiation. One is visible, which is the sunlight. The other is infrared, which is invisible, but it is equally as important to determining the balance of energy and the temperatures in the atmosphere. If you look at these numbers are sort of proportional to amount of energy coming across a unit area, averaged over time. That is, averaged over day and night and averaged over the seasons. We sort of get average conditions like this at the Earth's surface overall. And we can see here that of the solar radiation coming in from the sun, represented by that number, roughly half is absorbed at the Earth's surface, and we have a magnitude of 168. So if I stand outside in the sun, allow the sun to hit my hand, and wait a whole day and a night and a whole year, the average amount of energy I get from the sun is sort of related to this number down here. Now, if we go to infrared radiation, which is the invisible type, This is actually the way which most of the energy gets out of the system. We see some of the sunlight is reflected, but that's not equal to it. So the rest of the energy has to go out through radiation again, and this is infrared radiation. But there's a complexity here because the atmosphere is very actively reacting with this type of radiation. There's a lot absorbed, much more absorbed here than absorbed by shortwave. And there's also a lot emitted, given off by that gas, both in the downward and upward directions. The net effect is, if we look at this here, which is a measure of the downward infrared radiation coming to the Earth's surface here, we look at that number, 324 units compared to 168. That means if I hold my hand out and try to sense energy levels, I'm going to be receiving twice as much energy in terms of the invisible infrared as I would in the visible. And that is very much part of what determines how my hand feels. And it's very much part of how the Earth's surface conditions go. Basically, this back radiation here gives rise to an overall elevation of surface temperature over what it would be without this present. And that is the greenhouse effect. It causes enhancement of the surface temperatures due to these greenhouse gases right here. So that's where the carbon dioxide, nitrous oxide, ozone, etc., come into the picture. To the extent there's a definable increase in these directly related to the production of stuff from human activities, we then have a very definite effect on this. Now, this is not the only thing determining temperature. We'll get into other aspects which determine temperature, but it's a very important one. And it's the one which is most clearly in the positive sense, because I showed you those curves with the concentrations going up. They very clearly relate to the temperature condition. Now, another fact is that we're talking about climate change. It's not just the atmosphere we have to understand. We have to understand the ocean. We have to understand the land surface. We have to understand the life. Because all of these things relate to the climate conditions. They all relate to things like the carbon dioxide situation. We can be putting in stuff from our factories here. That's the source of carbon dioxide for the atmosphere. But that which we put in the atmosphere, some of it goes into the ocean, gets dissolved in the ocean. It's now estimated roughly half. Roughly half of this coming out here ends up in the ocean. So it sits in the ocean. And then it also might change conditions for life. And whether plants will take up CO2 or give it off, depending upon time of year and things like that. They all count. So it's impossible to discuss the temperature that we expect to have on land without understanding the temperatures and other processes going on in the entire system. And putting that into a model, understanding that interactive system, fully interactive system, is a huge challenge. You just can't do simple reasoning to say, well, let's increase the CO2, increase the surface temperature, increase the water temperature, increase the evaporation. Evaporation will increase the greenhouse constituents in the atmosphere and make it warmer. It's a positive feedback, so you get excited. You could also argue that we increase the CO2, we warm the ocean, increase evaporation, increase cloudiness, and the increase in cloudiness can reflect more of the sunlight and cause a cooling. You can argue anything you want, but the only true way to discuss this is to look at all these things in combination, simultaneously. And that's where we're really forced to go to these climate models that I'll be talking about later. So those are some of the facts. Now, I suppose I should say, if there is a question about these, please raise them anytime. Now let's look on to the next thing, which are the uncertainties. And here's where things really literally hit the fan. We're trying to understand what's going on. What I want to talk about are these various uncertainties, give some feeling for how serious they are. One is even determining how much effect we've had already in terms of changing the environment for the temperature. An even bigger issue is future emissions. Predicting the weather is hard. Predicting the climate system is real hard. Predicting people is the hardest of all. How can we predict what we're going to be doing in 50 years as a civilization? And that's one of the biggest uncertainties, and there's been attempts to try to get some hypotheses, and I'll talk more about these later on this one. Model predictions. I mentioned that the only way to get anywhere quantitatively with this system is to use these computer models that include the ocean, include the land surface, include the atmosphere, and I'll talk about some of the state of affairs with that. Model predictions for local conditions is a step beyond this, and we haven't even gotten to first base on that one. And then the impacts. Say the temperature does go up in Madison for 5 degrees in 100 years. How will it change things in Madison? I'll show you some examples where that's totally uncertain. Even if we assume a certain change of climate conditions, the impact on crops, impact on other things is, again, very uncertain. So this is like uncertainty to the fourth power. You take an uncertainty and you just amplify the thing. So that's a real challenge that we have in this business. Now, I mentioned uncertainty in even the current conditions. This is an estimate as to how the stuff we put into the atmosphere up to now, has changed the radiation, what we call the radiation forcing, how it has affected the radiation transfers in the atmosphere. And these estimates are shown here in terms of changes which would tend to cause a warming at the lower levels versus a cooling at the lower levels. We have been talking about the greenhouse gases right here. They have a definite warming impact. They've increased, their increase, which is measured, quantified, really expected to give a positive forcing on here. Now at this point here, I want to bring up one topic that maybe some people will mention to you. They'll say water vapor is the biggest greenhouse gas we have, and it's not even on the chart. Water vapor is the biggest greenhouse gas. However, it does not have a one-to-one connection with our factories and whatnot. Sure, we produce water vapor. Water vapor is coming out of the exhaust pipes of our cars. But most of the water vapor in the atmosphere comes from the ocean surface, etc. So we don't put that on this chart here. But it comes along in determining the overall impact, the end result. Anyway, these are positive. Ozone is also a greenhouse gas, but it has different impacts depending upon whether it's low level or high level in the atmosphere. And it does change with height, unlike these greenhouse gases, which are relatively uniform with height. Sulfates. I mentioned sulfate early on as something which is opposite, and here it is. It has a negative cooling impact upon the atmosphere. Aerosols. Aerosols up here, which is smoke, dust from fields, dust from fires, has a mixed reaction, but mainly negative. Mainly negative, but with huge uncertainties. These lines here show the level of uncertainty in this estimate shown by the bar graph. For the greenhouse gases, it's like a 10% of this thing. But for here, the uncertainty is equal to the magnitude, so it's a huge percentage uncertainty. But look over here. These lines, they don't even make an estimate. All they show here is the range of uncertainty. And this remains. The aerosol indirect effect remains something really to be understood. And what we mean by that, I'll give you an example. We put our smoke into the atmosphere. We put particulates into the atmosphere. These particulates run into a cloud. And in the cloud can change the characteristics of the drop sizes of the drops in the cloud, which then turn can change the radiative properties of the cloud for sunlight and infrared radiation. And that is not understood well at all. It's expected primarily to have a negative effect, but how big is unknown. And if you look closely, you can see that this line, if we have the maximum here, is almost equal and opposite to this. So these types of negatives here give a lot of room for people to sort of keep bringing up these things. There was a recent article here I have about the models don't have the forest fires properly in them, and the tropical fires do have an impact upon things. Finally, there's some smaller effects. You know, the airplanes flying through the sky often make these contrails, the clouds out the back, and sometimes they don't evaporate quickly, and you might get the impression that the sky is more cloudy than without the airplanes. And so there is a slight effect here, albedo effect and the solar effect. So these are sort of the uncertainties. But it also shows the number of different factors that we need to look at to get the whole picture just for the atmospheric condition. We're not talking ocean or land surface yet. There's a lot of different things that have to be put into this. Yes?
By solar effect, you mean the intrinsic variations in the sun?
Yeah, the sunspot cycle, the variations in the solar intensity are sort of put over here. I'm not an astronomer, so don't pin me down on that one. Okay, now, what are people going to do in the future? That's a huge uncertainty, the impacts. And I put here a little cartoon picture as to how they've tried to analyze this issue. There's been a whole study. There's another book as big as this one here, just analyzing scenarios for human impacts in the future. And this is sort of what they're thinking. There's various ways in which we can go in the future. There's an economic thrust here. There's an environmental thrust here. The economic thrust is deemed to sort of increase the impacts of these emissions, whereas environmental thrusts tend to decrease. Now, the things which determine, the primary things that will determine the human impacts on the environment are listed here at the bottom. These are sort of the roots. The population, the energy that we need, relates to the population very directly. The economy. A good economy can change things to more pollution of the atmosphere. I'll show you an example in China where a poor economy in the last few years actually decreased the amount of pollutants. Technology. Are we going to get clever at producing energy or not? Depends how we produce it. And there's also the agriculture. So trying to come up with estimates and discussions of these issues is a huge problem. Now, just to show one example, one part of that, I'll look here at the population projections that have been recently issued for the whole Earth. And these go with different scenarios, which just different scenarios, different curves. Here's where we are at the time of the start. And you see that some projections have the population going from almost 6 billion here up to maybe 3 times in this case by the year 2100. Others less, and some even have it going down. And so this is the first time I've actually seen evidence, serious discussion about there is a possibility that we can actually have a stabilization of the population. And that will have a big impact upon the types of things that will go on. Now, to get a little bit more specific about these hypotheses, these are described a little bit more in the handout, but it all relates to how much fossil fuel we use to get energy versus other forms of energy production in here, whether it be a focus on oil and coal or something else. It gets a little bit interesting here because it's recognized that nuclear energy does not produce the CO2, whereas oil will. So there's an argument to switch from oil to nuclear energy, but then there's other issues that come up. So it gets a little complex. Also, whether or not we try to go as a world or stay separate. To the extent the whole world tries to come up to the standard of living of the U.S., we're going to get extremely large increases in the effects on the atmosphere, whether we have a clean technology or not. And so these are the various descriptors of these hypotheses that we have for the future conditions. Now, how much effect do these have? I'm not going to put the descriptions on. They're in the handout here. But here are the effects of these theories on the emissions. The emissions now measured in terms of the forcing, which is the same thing I used on that earlier chart. Basically, this is sort of like compared to the present. The present is half a unit on here. And here are the different scenarios. And you can guess that the B ones, which were not so bad, will give rise to curves like this, whereas some of the A ones give rise to this. Tremendous increase in the forcing of the atmosphere over what we have now. And that's what we're talking about, the 21st century, what will it be like at the end. Okay, now, just a quick word about the models. I don't want to skip over it, but here's a word about all these climate models that we use to try to estimate how the climate itself will change if we change all these emissions going into the atmosphere. There's roughly 20 or 25 climate models in the world that have been focusing, at least part of their activity, on studying projections for future climate of the world due to human impacts. These are maybe, well, they're not all United States. There are many other countries do have these, but there's a large number in the United States. What they did to try to estimate how the models were consistent with each other was to give all the model groups a specified change in these forcing parameters to put in their model. You specify that, and then they were asked to make a prediction 80 years out and see how their global mean surface temperatures looked. And that's what we're looking at. This is the global mean surface temperature change from the beginning of the experiment going out 80 years for the different models. And you notice here, some model here change only 1 degree Celsius. Model here change 3.5. That's quite a variation for a model which is supposed to be a quantified projection of things. So there's a range of at least 2 to 1, just due to the model formulations. And there's a lot more work that needs to be done on that. Precipitation's even worse. We don't usually talk about precipitation as much, but this is the way the models have shown it, at least at the time of this. They do show generally an increase in precipitation over time, which is consistent with my statement was that the increase of temperature means an increase of water vapor in the atmosphere, and so the increase of precip sort of makes sense. But in this case, starting this time, some models didn't change at all, and some models changed by 7%. So the range, the difference between the models here is even bigger than for temperature. Yes?
I've heard in models like this that the degree of error, like in the climate and temperature change models, can be as high as like plus or minus 2 degrees. Is there truth to that?
Well, you see that here.
Right.
Here, -2. You almost see that right in here. So it's true. It's true. Okay, now, if we put together all these different models and all these different scenarios for emissions, this is sort of the end result. This is now temperature change predicted by the models for the range of these scenarios for emissions here. And there are... You really need to have this in color to see the details, but we see that the range is roughly from 1.5 degrees increase by the year 2100 to 5.5 degrees Celsius now increase by the year 2100 with the majority of calculations coming into the middle of roughly 3. So when reports were published in the paper, you might have seen reference to a projected increase sort of in the range of 3 degrees Celsius, which is about 5 degrees Fahrenheit, but again, a large variability. So that's where the most recent report has put the projection. Now, for local temperatures, I'm not even going to put up any examples of the local temperatures. They looked at the same models, and they looked at just the temperature predictions for a sub-region, not the whole surface of the Earth, but a region. And the variations in there were so big that it's embarrassing to show. Even comparing the control case, that is, to take the model, put in current conditions, run the model and see what the climate is, compare it with the observed climate of temperature in small regions, is very, very, very hard to get anything that looks workable, let alone talk about the changes in these local temperature conditions due to changes in the atmospheric conditions. So I won't even show that, but it's certainly an area that has to be addressed, because in the whole climate change business, the city of Madison really is interested in what Madison is projected to be for the year 2100, not what the global surface temperature is projected to be. Everyone needs to know something about the local conditions in order to make a meaningful advance in doing anything for this. And that is a lot of work is needed to get to that point. Now, I mentioned the impacts given a change. Let's say you give it a 5-degree change, how will it affect things? There's a lot of uncertainty there in itself. And these are the various things that are looked at in terms of what will change if we change the temperature and change the precipitation globally. We have agriculture, forests, the deserts, the water supply, ocean sea level, human systems. There's a lot of things. The energy industry, how that will be changed if we change the climate. There'll be large economic, insurance changes projected. Human health. There's a lot of things that could change with human health if we change the climate conditions. You've heard of this Nile disease that's coming up through Illinois. And there's other things coming up from the south. As the temperatures get warmer, more and more of these subtropical, tropical diseases will get into here. Finally, the weather itself will change. I've been focusing on average conditions, but we talk about extremes, storms and weather. They can be much more dramatically changed compared to these average conditions. So that's the range of things that we have, and there's uncertainties. I'll just show two. And I'm not trying to embarrass the agricultural people, but you know, they're all in the same boat. Here's an example for a study for South Asia on certain crops, wheat, rice, etc. And what they did, they put into their crop models changes coming from these climate models projected in the future. And I showed you some of like the global mean temperature changing. They put these numbers into their crop models. And here's an example for Pakistan wheat. The estimates for changes in Pakistan wheat yield from minus 61% to plus 67%. Now, where does that leave you? I mean, there's no new information there except that we really don't know how to do it or what to do. There's such a range. Even, will it get better or worse? We know that in climate change, some things will get better for people and some will get worse. But we can't even get very far with discussions when we have such variability in figuring out what really is the impact of these things. I also mentioned tropical diseases. Well, here's just a summary of some of these diseases which are vector-borne. In other words, mosquitoes and other insects carry the disease, and where those insects go has a real relationship to the climate. And it's just summarizing here these things which are tropical, but to the extent these things might be creeping poleward, or even getting worse in those countries, there's a lot of people that could be impacted by this. in effect. So that's something that we keep in mind. Okay, now I want to sort of change the tune a little bit here and talk about the challenges. We're not giving up. We can't give up. So the challenges, let me just summarize a little bit here. Big challenges, we have to consider the entire climate system and all of humanity in order to move forward in any of our work. We have to remember there's extensive natural variability, which is always there, and it sometimes makes it difficult to isolate the human-produced things. Global connections. That is, if we in Madison make a lot of extra pollution, it's going to, to the extent it's like the greenhouse gas pollution, it will affect the levels over the whole world. If China does the same thing, it affects life here. So we're interconnected. Some things, fortunately, we're not so interconnected, and that's like aerosols. If you've been in some countries that are heavily polluted, you thank God that pollution doesn't spread itself evenly around the world and ruin it for everyone. So the uncertainties involve outcomes from uncertainties in many different components. I've been through that. I didn't say anything specific about the changes in extremes that are expected, but there have been studies that really show, for instance, the occurrence of drought in the Midwest could go up a substantial amount or down with the climate change conditions. Need for research. Well, we obviously need a longer data record. I showed you 100 years. And in terms of climate change, that's a pretty short time. So for some of these things, we have to wait. We just have to wait. But we can't wait to do something about it until we have enough record to make the point even clearer. I mentioned the theory. The theory about radiation and cloud droplets and whatnot is really quite incomplete. The models, I showed you how the models varied in their performance. Well, there's certain aspects of the model which are still not even fully defined. How do we represent a thunderstorm in a climate model? How do we represent small features, which are important in the overall climate? Separating natural-induced fluctuations from human effects is an important challenge, and I'll say a little bit more about that. The nature of people. The nature of people is how do we control ourselves? Even if we identify this effect, how do we control ourselves in terms of pollution? How do we get world cooperation? How do we change our own lives to the extent it might affect the release of greenhouse gases and other things into the atmosphere? I'll show you one study which just appeared in the recent edition of a scientific journal here. They asked 19 experts in the field of the climate change, 11 from the U.S., the rest from other countries, to look at the data, to look at certain data. And they had 4 types of things they wanted to focus on in the data. One is the long trend, which I did show you, in global mean temperature. The second is a change in the vertical pattern of temperature. I did not show you that, but it's basically a change where it's getting colder at the upper levels and warmer at the Earth's surface. A change in the geographical pattern. I did not show you that. That's saying that the warming that we're seeing is more at high latitudes, it's more over continents than over oceans, and it's more in the cold season, and it's more at night. That's where the warming is really showing up most. So seeing how that relates to feelings that it is a human impact. And finally, the trend in diurnal temperature range over land. So we have data on these, and the experts, using all their probability thinking and theoretical and whatnot, looked at these records to make two determinations. One is can we say there has been a change, a significant change, a meaningful change in these characters here? And for the number 1, 95%, this is a median, the mean by the 19 experts. There's quite a range among them. 95% yes, they are saying there is detection of a warming. And I showed you that very first curve. 99% saying this trend in vertical temperature, which I didn't show, is very discernible. 80% thought that the pattern of surface temperature was discernible, and only 73% this diurnal thing. Now, the next question was, for these four things, how much was attributed to greenhouse forcing? That is, how much is attributed to human impacts? 72 that is almost 70% of this trend that I showed you, according to the way they analyze it, is due to human impacts. So this is a quantitative estimate of the relative difference between human impacts and that which can't be explained that way. Only 20% felt that the vertical pattern of temperature was due to the greenhouse theory, 61% for the geographical patterns, and 45% for this. So I'm just giving you some specific numbers that's in the thinking of people. Because if someone were to ask me, is that temperature record evidence of climate change in terms of climate changes due to human activities, I wouldn't have said yes or no. I would say yes at a certain level of confidence. In other words, it's a statistical thing. And you're seeing the same type of thing here. These are mean expectations, and it's something that we're trying to do. And we, of course, hope to narrow the range in time.
There's an interesting thing there that they had that a 30-year trend in vertical pattern temperature.
Yes.
99% of the experts of the mean was 99%
Believe that there was a change.
But the expected fraction is only 20%, which is interesting.
Due to greenhouse forcing, right. Yeah, and I'm not prepared to explain the details of that variation, but that's the way it came out.
It's interesting with other figures, though.
Right, I agree. Yeah, there's other things that could explain the vertical temperature structure. There's other ways for energy to go up and down. So it's complex. All right, now what can we do about this? I sort of end up here with a few statements about what can we do about climate change. I'm not speaking here as an activist for environment, but it just gets you thinking about things that are there. Why should we care? How can we modify our lifestyle? Mitigation and adaptation. I won't say much about it, but mitigation means how can we reduce the climate change impacts, or how can we adapt to whatever is going on to keep going. There's two ways one can approach the future, or some mixture of these two. Of course, modifying national and global practice, Kyoto treaties and all that is a very complex thing, and we as people have very little impact upon that. Influencing public policy. I hope that everyone here has a little role in that. You know, you express your feelings and whatever to the representatives or the public officials. So let me just give a few examples here of some of the details. Why should we care? Well, let's put the title on here. Why should we care? Well, we do feel pretty confident that there are changes going on due to human impacts. Now, the question is, are those changes good or bad? That's not answered here. We suspect some will be bad, like the disease business. Some countries will have worse conditions for living. Some may have better conditions. We do expect that the heat waves will rise. So these are some things, just some things that one can think about as saying, why should we care? It's going to impact us somehow. And these are just some examples of things. Economic, there might be billions of dollars in property damage. There might be billions in profits for the air conditioner manufacturers. So even the economics, is some pluses and minuses. So these are just basically food for thought. One thing that's all behind this is energy, the production of energy for various things. And it's useful just to see what we use energy for. And this is an analysis done way, way back. But it's still relevant today in saying that if our energy use is this green circle here, there's not one part of the sector which is responsible for most of that. It's spread around. We talk about industrial. We've always focused on industrial stuff. But the residential and commercial and transportation are equally big blocks here in terms of energy requirements. So we just can't all put off on the companies here. If we talk about our homes, whatnot, this is a little inaccurate. The air conditioning one is too low for now, but it's different things. So you try to say, where can you be more efficient? Well, if you can be more efficient in space heating, maybe that's going to have a bigger impact than being more efficient in the lights. I'm very, very general here. In terms of transportation, this will go again in 1972. Running our cars around is sort of half the thing. We like to blame the trucks. We like to blame trucks for things, but in terms of the energy use is less. And the airplanes have obviously increased since this thing was made here. But now what I want to focus on is the efficiency of energy use. It's interesting that the auto is more efficient than the rail. I found that interesting here. And the air is way down here. So, but we're going towards the airplane. This is in terms of gallons of fuel per passenger mile of transported. So if we think of the efficiency, yes?
My understanding is that those figures are seriously out of date, and mass transit is now about comparable to automobile.
This one here.
Mass transit has gone down, and cars have gotten more efficient.
What about air? Do you know how air's changed?
No.
Okay.
But there are figures published, federal figures published every year that you can get in the engineering library.
Okay, thanks. I better look it up for the next talk. Let me just look at the freight one. The truck versus the rail versus pipeline versus waterway. The waterway is obviously, according to this, the most efficient in terms of the amount of fuel needed to transport so many tons of fuel. So this is something that often isn't really put in one picture. We like to attack a certain part of our system as the place to clean it up. And it's important to see the whole picture. So now this is given out by an environmentalist group. It's sort of interesting, indicating here some changes you can make in your own life. And then there's an estimate here of how much carbon dioxide is reduced. Now, I don't claim to justify or understand where these numbers come from. But the thing which I noted was how big these numbers appear to be. And but I'm not prepared to defend them. But you can do stuff like this to see where do you want to do your thing in terms of the carbon dioxide. Now, so we come up, what can we do about global warming? Well, again, this is related to the last thing, things you can do. And as individuals primarily. This doesn't get into things you can do by trying to influence public policy and whatnot, which can also have an influence. Now, one last thing to end up. I mentioned earlier that the China actually was able to achieve a reduction in greenhouse emissions. This is published in Science magazine based upon a number of authors here. And they show over here for the total emissions of carbon dioxide increasing up to 1997 and then decreasing down here. So there's an example. I showed you an example early on of the sulfate peaking and coming down. Here's an example of this carbon dioxide doing the same thing. But the authors of the paper point out that there's a lot of economic reasons why this happened. It wasn't any explicit policy trying to independently turn off manufacturing and whatnot. It just happened. But it does show the impact upon economy on things in general, no matter what other kind of policy we have. So that is sort of the broad brush picture, and I hope you get some general perspectives. Some of the details may be very specific, but the general perspective of the overall complexity of the situation and the challenges that we have yet to face. It's going to be a sustained effort needed over many, many years to get some more clarity on some of these issues. And to the extent that we are actually assuming we are in a warming trend or a change trend, it is important that we get some handle on these, more quantitative on these things to help people think about what to do. So that is it.